Hello, good afternoon, everyone. Thank you for joining us for the fourth FHERITALE webinar today. It's very exciting to have all of you here. We've got a great lineup of speakers for you today. We've got Robert Wils from Agilent. We've got Junli from University College Dublin and Juliette Legler from the University of Utrecht, all of whom are going to give very exciting talks. But first, I'm just going to quickly give an overview of the FHERITALE project before we get started. So if I just share my screen. Okay. So here we have an overview of all of the research infrastructures involved in the FHERITALE project spread throughout Europe. We have Anaï based in France, Irene based in Massaric University and Utrecht University, Instruct-ERIC, and Metrofood based in Italy. Now, the goal of FHERITALE is to set the ground for providing the European scientific community with easily accessible services at a single point of entry to facilitate the study of artificial materials on a micro and nano scale. Today, we'll be talking about microplastics, but that also applies to other artificial materials, for example, plastic additives, bioplastics, and metals, and studying their effect on health, food, and the environment. The main activities of the project so far have been mapping services available to researchers, as well as identifying service gaps and technology needs, and making strategies for increasing service availability and promoting interdisciplinary research with a One Health approach. If you would like to know more, for example, look at our social media pages, our existing webinars, or all the information that we have on our website, then you can scan this QR code in the bottom left here. That will take you through where you can find all of that information, including any upcoming events that we may be having. Thank you very much. So now I'd like to hand over to Robert Wils from Agilent, who will be starting us off. Great, thank you very much. Over to you.
Yeah. Hello, everyone. So I'd like to just begin by thanking Ryan and David from Instruct-ERIC for giving me the opportunity to speak with you today. So as you can see, this presentation focuses on microplastics analysis and specifically using the laser direct infrared imaging spectrometer that Agilent introduced onto the market about 5 years ago. So I'll start by giving an overview of the LDIR system and explaining how it operates in the context of microplastics analysis. And then I'll share some results with you from a recent study in which we really pushed the system to its limits to answer one of the most common questions that we get asked, and that is, what is the smallest particle size that you can reliably detect? Let me begin with a few observations about microplastics measurement. It's an exceptionally challenging application, arguably the most challenging that I've encountered in my 30 years in the analytical measurement business. As you all know, the particles themselves are extremely small, but certain polymer types, like car tire debris, for example, are just inherently more difficult to analyze than others. But when you also consider the wide range of particle shapes that are commonly encountered, then the complexity of the task really increases significantly. Importantly, there is no single technique that provides a complete answer. So most laboratories working in this field rely on a combination of complementary tools. So for example, techniques such as pyrolysis GCMS or thermal desorption GCMS are highly effective for identifying polymer types and for generating accurate mass-based data. However, these methods are destructive and they can't provide information about particle count, size, or morphology. So to obtain that level of detail, spectroscopic techniques are required. And in recent years, Raman and FTIR microspectroscopy have been widely applied to microplastics analysis, each offering distinct advantages and limitations. Raman spectroscopy, for example, can resolve very small particles down into the sub-10 micron range, but it's often affected by sample fluorescence. Infrared microscopy is generally more cost-effective, but it's less sensitive and it's typically limited to the analysis of larger particles. What both techniques have in common is that they're relatively slow, They're only moderately automated, and both require a high level of operator expertise in order to achieve optimal results. So this is the LDIR. It doesn't look like a traditional microscope, but appearances can be deceptive. It is in fact a very highly powerful infrared imaging system that combines the best attributes of both Raman and infrared microspectroscopy. So like a Raman instrument, the LDIR uses a laser source, so specifically a quantum cascade laser. And QCLs operate across a portion of the mid-infrared spectral range, but unlike Raman lasers, they're not so powerful that they induce fluorescence. But their emitted infrared light levels are significantly higher intensity compared to the glow bar sources used in infrared microscopes. A key advantage is how the energy is delivered to the sample. So in an infrared microscope, the beam is spread over a relatively large area, whereas with the LDIR, we can focus the laser into a tightly defined spot, approximately 5 to 10 microns in diameter, and that concentrated power can be directed onto individual particles, which results in high quality spectra with excellent signal to noise ratios, even for very small particles. And you'll see that for yourself later in this presentation. If you were to look inside the LDIR, you would see that there are two separate measurement channels. So at the front of the instrument, there's an ATR objective, while at the back of the instrument, there's a reflectance objective. For microplastics analysis, the ATR mode is very rarely used because it requires physical contact with the sample, and that can cause problems as the particles adhere to the crystal. So instead, we typically use the reflectance channel, and this employs what we call a flying objective that rasters across the sample surface at very high speed. So the measurement itself is entirely non-contact, and the reflected infrared signal is detected using a thermoelectrically cooled detector, which means that the LDIR operates without the need for liquid nitrogen. To illustrate the importance of image resolution, I'd like you to consider the example here of the Mona Lisa. So the key factor here is the pixel size. Smaller pixels produce higher resolution images, while larger pixels result in more coarse or grainy appearance. In infrared imaging, higher resolution comes at the expense of acquisition speed, so there's always a trade-off to be made. With the LDIR, the pixel resolution is adjustable, ranging from as fine as 1 micron, yielding very highly detailed images but at slower collection times, to as coarse as 40 microns, which enables much faster acquisition but with reduced image sharpness. So at first glance, that raises an interesting question. If the laser spot size is fixed at 5 to 10 microns, how can you get a 1 micron pixel size? Well, the answer to that lies in the use of a technique known as oversampling. So this involves collecting a series of overlapping measurements, effectively reducing the pixel size below the physical spot size of the beam. So oversampling not only enhances image resolution, but it also improves signal to noise ratio as the signals from the overlapping regions are averaged. But in addition, it enables more precise definition of particle edges, allowing for more accurate determination of particle size and shape. At this point, I think it's only right to point out that the sample measurement is only the last step in what is typically a much longer process. So clean samples like drinking water only require simple filtration prior to measurement, but more contaminated samples such as wastewaters and sludges will require extensive preparation in order to extract the microparticles and pre-concentrate them into a small volume of solvent prior to filtration. For very highly contaminated samples, the use of low E slides, also known as Kevlar slides, are a good option. So these slides are the same size as conventional microscope slides, but one side has a infrared reflective coating applied to it. And these slides are useful because by spreading out the contaminated sample over the whole area of the slide and allowing the solvent to evaporate, you can reduce the risk of particles aggregating together. For most organizations who choose to purchase the LDIR, the big attraction is really the automated workflow, which makes the system very easy to use and it helps to maintain a level of measurement consistency and reproducibility across all units. So the workflow starts when the user inserts the sample and closes the door, and that's essentially the only interaction that they have with the hardware. The sample is shuttled to the back of the LDIR where the reflectance channel is located, and en route it passes through a light curtain which creates a side profile view to ensure that the sample is flat. It also passes underneath a wide field visible camera which automatically collects a picture of the sample, and this is then displayed in the center of the software screen. And it forms the basis for how the user interacts with the Clarity software. So for example, users can zoom in or out of the image just simply by using the mouse wheel. The user then selects the method that they want to use for the analysis and the spectral library that they want to compare against. And then they can draw a circle or a square or a rectangle around the area of the sample that they wish to measure. The laser is then fixed at a specific wavelength that corresponds to the CH stretching band found in all polymers, and the beam is rastered across the sample at very high speed using the oversampling approach to collect at 5 micron pixel resolution. This fast scan not only detects the particles, but it's also enough to characterize their size and shape. And the use of that specific wavelength that only occurs in polymers helps to screen out any non-polymeric particles that may still be present in the sample. With the particles detected, the LDIR then focuses the laser on each particle in turn and collects a spectrum and processes it against the library in order to identify the polymer type. And that all happens in just a few seconds per particle. And the identification results are compiled in real time into histogram reports that show the distribution of polymers by type and by size. And you get a list of all of the particles with an image of each one, showing and the details about the library match quality and so on. All of that information can also be exported as a text file, and that can then be imported into Excel, for example, or into any kind of specialist reporting tool. So now let's turn our attention to the tests that we conducted. So in order to explore the limits of the LDIR, we brought in some certified standards of polystyrene beads in sizes of 10, 5, and 2 microns. And we deposited aliquots of these standards onto both aluminium coated filters and low E slides. In the automated workflow, the user can set the minimum and maximum particle sizes that they're interested to detect. So for the 10 micron beads, we set the minimum to 10. For the 5 micron, we set it to 5, and so on. Users can also define the criteria for the hit quality of the library searches. So the matches can then be scored as high, medium, or low quality. For the manual workflow, we set the system to do the initial raster scan at the 1 micron pixel resolution setting. And then we examined the resulting image and collected line scans across a selection of individual particles, which were then averaged and searched against the same library. On the selected particles, we also collected very high resolution visible images in order to determine the size of the beads. So the results looked something like this, starting with the 10 micron beads. They were easily detected using the automated workflow on both the filters and the low E slides, because these beads are larger than the default 5 micron pixel resolution used in the automated workflow. The hit quality of the library matches was also very high, with almost all of the match scores falling into the high confidence category. And the particle size estimation was also pretty good, with the average size estimated at 12 microns. The manual approach also gave really excellent results on the 10 micron beads. So again, on both substrates, the quality of the library matches was actually slightly better than for the automated workflow due to the spectral averaging. And the size estimate of the particles was also more accurate because the visible image is a little bit sharper than the infrared image. For the 5-micron particles, the automated workflow again works surprisingly well, but it's worth noting that along with the polystyrene beads, it also detected a lot of contaminant particles from clothing and skin, because these trials were not conducted in a really clean environment. Nevertheless, the majority of particles detected on both substrates were the polystyrene beads, but this time around there was more of a spread in terms of the quality of the match scores, as some of the matches were ranked in the medium or low confidence category. Again, the size of the particles was slightly overestimated at an average of 8 microns. In manual mode, the results were again really good for both substrate types, so slides and filters. The library match scores mainly fell into the high confidence category, and the size of the beads was accurately estimated at 5 microns. And now for the 2-micron beads, the results of them, or should I say results singular, because in this case, these beads were simply too small to be detected using the automated approach with the 5-micron sampling interval. Using the manual workflow, we also failed to get any sensible results using the aluminium filters because of interference from the pores in the filter. But we did get results from the low E slides, and really good results too, with the quality of the spectral matches remaining in the high confidence category, and the size estimate is bang on the money at 2 microns. So in conclusion, the LDIR's automated workflow operates really effectively on the 10-micron particles, and it can even be used to collect data on particles down to 5 microns. But this is really at the limit. Using a manual approach, you can measure particles smaller than 5 micron, but the choice of substrate is obviously more critical. But together, the two workflows can be used in a complementary fashion. So the automated route can be used for fast collection of data on high numbers, and the manual approach for more in-depth studies on smaller subsets. So all of this data I've just presented is detailed in a technical note that's freely available to download from the LDIR pages on the Agilent website at www.agilent.com. And here you'll also find a wealth of other publications related to microplastics analysis using this technique. So that ends my presentation. Thank you all for your attention. I think we still have some minutes left, so if anybody has any questions, I'll be very pleased to answer them.
Thanks very much, Rob, for that presentation. Yes, if there's any questions, please feel free to type them in the chat. But if not, maybe I can get us started with 1 or 2 questions. And likewise, if you'd like to ask a question out loud, please raise your hand. So to begin with, I just wanted to ask a little bit about the throughput of the technique, because I think you mentioned a couple of seconds when analysing the particles to characterise them chemically and to ascertain their identity. And how many particles is it typical for researchers to measure for one sample? And if they have multiple samples, are there options to sort of help with the throughput of the process that you're aware of, or is this something that's the next thing?
Sure. No. Yeah. So great questions. So the time taken to measure a sample is limited only by the number of particles in that sample, right? So if you're measuring something like a relatively clean sample, like a drinking water sample, where you would expect there to be only a few tens of particles, then it's going to be very quick compared to a much dirtier wastewater that contains thousands of particles. So on average, the system cracks through about 800 particles per hour. So for a clean water, like I said, that's a few minutes. For a wastewater, that would be a few hours. But the point is that the system is collecting and compiling the data in real time, and you get a very optimized measurement on each specific particle. In terms of the throughput, you saw in the picture that there's a there's a holder for filters with 2 positions, so you can queue up 2 samples. But you can also put the filters onto the low E slides, and then you can queue up multiple. So you can get 3 25mm diameter filters on a slide. Or if you use smaller filters, which some customers do, especially for the cleaner samples, then again, you can get multiple filters and just queue them up so they automatically measure one after the other.
That's great. Thanks very much, Rob. We've got a question from Sapana. If you'd like to unmute yourself, feel free to ask a question. I can't hear anything from my end. Maybe you could type.
You're still on mute, Sapana.
Maybe you could type the question in the chat, and Rob will be able to answer. I've got one more question. In the interest of time, maybe I'll go ahead and ask. I wanted to ask Rob about standards, with that being a big topic in the field at the moment, I guess. And what standards would you use in terms of your polystyrene microparticles, and are these pristine? Because obviously particles in environmental samples. I think we've got Sapana now.
Hello. Hello, can you hear me?
Yes,
we can hear you.
Okay. I would like to ask that where will we get this facility? Means sort of any institution or anything, particular institutions where this facility will be available. Can you tell one such example? So that I work in microplastics, but using different flow cytometry and other.
So sorry, Sapana, it's really difficult to understand you.
LDIR. I have used FTIR. I have used Raman, but I have never used LDIR. So I'm asking, where can we use this facility? Just to get an idea of how it's working.
Yeah, I'm sorry, Sapana. There's a lot of feedback, a lot of echo on your microphone. So it was really difficult to understand that. Maybe Sapana, if you type it in the chat box.
I'd suggest typing it in the chat box, and perhaps then any other questions for Rob can also type there, and I can see them coming in now. And then maybe we can move on to our next speaker as well, so we stay on time. Thanks very much, Rob. That's great. Very interesting.
Welcome.
But with that, maybe we'll progress to our next speaker, who I can see has come on screen now, Professor Juliette Legler, who's going to talk a bit about the Momentum project, Momentum 2.0 as well. So looking forward to that, Juliette.
Thank you very much. I really appreciate the opportunity to come here and speak for you and this FHERITALE Consortium. This talk will be quite different than the previous two fantastic talks, which really went right into depth and detail about the analysis. I'll give you a bit of a bird's eye view of a big program that's ongoing in the Netherlands. So let me share my screen, and if you have any questions and we run out of time, please just get in touch with me, and I'll also bring you in contact with the scientists doing the research. So I've been coordinating this Momentum Microplastics and Human Health Consortium since 2021. And today I wanted to show you a few highlights of our first 5 years of research and our plans for the coming 4 years. Just to check with you, are my slides okay? Can you see my screen?
Yes, we can see it.
Thank you.
It's great.
All right. So Momentum is a vibrant community of researchers, representatives from industry, government, NGOs, a really intersectoral and interdisciplinary group of scientists who all have in common that they want to learn more about micro and nanoplastics and potential health effects on human health. So the picture on the top left here is the ending of the Momentum 2 project in July of last year, where we had over 100 participants in our final meeting. And we're lucky that this work is still moving forward. You can see here the evolution of our projects that started actually as small individual projects back in 2019, funded by the Netherlands Organization for Health Research and Development. And after those first high-risk, high-gain projects took place back in 2019, The funder had this amazing idea to bring all of these different projects together into one big consortium, and that's how Momentum was formed. And so in 2021, we had our first Momentum project. In 2023, Momentum 2.0, and just at the end of last year, Momentum 3.0 started. The consortium is made up of over 30 partners from the Netherlands and Belgium. We are universities, and for me, this is the first time so many Dutch universities have worked together in one consortium. Usually we're competing with each other, and now we're working together, and that's just been really special and great for all of us learning about this complex field of microplastics and human health. So we're also a number of research organizations, hospitals. Our funding goes directly to the academic partners. However, up to 25% of our funding comes from the international private sector. Those are in-kind and in-cash investments from SMEs, large enterprises, and trade organizations. We also have some advisors from NGOs, Dutch ministries, and from the private sector as well. So like I said, all sectors are represented here in this large consortium. The goal of the Momentum program is really to do fundamental research to unravel human health risks of micro nanoplastics, but also to develop better risk assessment approaches, new risk assessment approaches, and also to already think about solutions to reducing exposure and health impacts, even if we don't have all of the answers to all of our questions yet. Last year, we put out a flyer on our key findings in the first 5 years of the project. You can find these on our website, momentummicroplastics.nl. And what I thought I would do today, given just the short amount of time I have, is just to show you a few of the highlights, which are certainly not exhaustive for this large program. So I'll take you through the different highlights using this cartoon here as a guidance. So the first thing we really needed to do when we started out 5 or 6 years ago was to have some reference particles to do our toxicological studies with. And that's why particle production and characterization became one of the major themes of the project. We were very lucky to work together with TNO, and TNO took on the charge of producing reference micro nanoplastics for toxicity testing. And they did this in a top-down manner, grinding and milling and sieving and producing fractions of plastics for us, as well as leachates. And these were distributed to 14 partners to do toxicity testing. You can find the protocol for how TNO created these reference micro nanoplastics at the link below. We have a special issue in the journal Microplastics and Nanoplastics, all about momentum research, where you can find many publications, what I'm showing today. So we focused on polyvinyl chloride, polyamide, and polypropylene, in addition to commercially available polystyrene. TNO, as well as the companies Wesseling and LyondellBasell, provided us with the plastic and also helped us make these reference particles in the different fraction sizes to do the toxicity testing. We also compared our effects with micro nanoplastics with some other non-plastic particles like titanium dioxide and talc. Importantly, we characterized these reference micro nanoplastics. We developed so-called sample passports, which gave a really good overview of the different characteristics of the plastics. You can find these sample passports on Zenodo at this link here. And I'll just contact me if you don't have time to take these links. So we'll try as much as possible in this project to provide a lot of our background information online and on open access, so we can all learn from it. I'll move really quickly to the hazard characterization part of the project, where we use those reference micro nanoplastics to test the toxicity in various human cellular models. So we did not do animal studies. We did all in vitro cell culture studies using human cells of these different tissues you see here on the slide. And to summarize 5 years of research, it's some of our main results indicated that from all these tissues, The lungs seem to be the most sensitive tissue in terms of the lowest doses were needed to cause toxicity in these models. Of the 4 or 5 different plastics we tested, the polyamide 6.6 was the most toxic. So there was quite some difference in the toxicity between the different kinds of plastic particles. And chemicals leaching from polyamide also seem to be toxic in our lung cells. So again, lots of this information is published in the Momentum Special Collection or on its way. And just to show you one highlight from one of the PhDs, this was also an amazing project that many different young researchers were involved in receiving their PhDs or postdoc. And here's an example of Irene Gosselink's work. Irene will defend her PhD 2 weeks from today. And Irene looked at the toxicity of our micronanoplastics in human bronchial epithelial cells. In this case, she showed that polyamide was the most toxic and that it caused toxicity to these cells, especially in the smaller sizes, the smaller fraction sizes, and also induced inflammatory reactions in these bronchial cells. I'm moving forward to the exposure. So in addition to trying to understand the hazard in our human cellular models, we also wanted to get a better idea of internal exposure. And in contrast to some of the work showed by my colleagues earlier today, we focused mainly on pyrolysis gas chromatography, mass spectrometry, pyrolysis GCMS, to quantify micronanoplastics in blood. So this was done by the group at the FHU, the Vrije Universiteit in Amsterdam, the group that first published on pyrolysis GCMS in blood, and they optimized their methods during the Momentum project, published and used these methods to measure, I think, one of the first applications of this approach to human cohorts. And this is an example of the results coming from that work. So within one of the birth cohorts in our consortium, we measured micronanoplastics using pyrolysis GCMS in 100 samples. And we also looked at immune reactions in these blood samples. And the postdoc, actually PhD, who's just started her postdoc, Amanda Durkin, working on this project, showed that the concentrations of MNPs in blood were associated with a higher expression of various cytokines and immune markers in blood. However, no associations were found between micronanoplastic exposure and lung function. It was a small first cohort study, but I think it's really important proof of principle that we can scale up some of these exposure analysis techniques to look at real human cohort studies. We wanted to develop risk assessment and solution routes in this program. Here's a very complicated slide about how we brought together all of the different work packages in the Momentum 2 project to do preliminary risk assessment. So on the left side of the slide, you see the different approaches to tackle exposure. First, to understand the fate of micronanoplastics in the environment, and then to model the major external exposure pathways for humans. We then measured internal exposure in blood and in different tissues. On the right side, you see how we went from looked at the hazard from using those reference particles. As I didn't mention before, we used both virgin and weathered particles, and we also looked at the biocorona on the outside of micronanoplastic particles. We did hazard assessments with new approach methodologies, limited animal studies and epidemiology, and modeled how these particles travel through the human body by developing biokinetic pharmacobiokinetic models. This work has led to some of the first preliminary risk assessment estimates. The approach is described in the paper shown here below, again in the special collection of our Microplastics and Nanoplastics publications. And basically this work showed that again, the lung is really appeared to be the most sensitive tissue, and indoor air seemed to be the highest exposure route for exposure to micronanoplastics. And so we will be continuing with that work in Momentum 3. And again, if you'd like to find some more information on our projects up till now. Again, our website and our flyers are showing lots of information, including how we developed a strategy for solutions. I just want to briefly tell you that we started Momentum 3 at the end of 2025, and as I mentioned earlier, focusing on risk assessment of micro nanoplastics in indoor air. So looking at inhalation exposures, and not only on trying to better understand the exposure and effects on the lung, but also we're developing technical and behavioral interventions. So really looking at solutions research in this new phase of the Momentum evolution. So finally, we have this vibrant interdisciplinary community. We really want to keep everyone together and working together. We've developed what we call the Momentum Collaborative Network on Microplastics and Health Research. This collaborative network is really meant to keep expertise together, open for international partners to join, to share data and knowledge, to help each other provide access to equipment and approaches, collaborate in new projects and initiatives, provide scientific evidence, provide training for the next generation of researchers. So here's an example of our next gen early career researcher network. So we've started it again with this network in Momentum 3, and we're open for anyone to join the network who would like to have their ECRs be involved in training and all sorts of activities to build a network and to build the next generation of microplastics and nanoplastic researchers. So that's my final slide. Please consider joining our network, or if you are already in a network, see how we can join networks together. We have a stakeholder meeting coming up on the 10th of July in Utrecht, open for anyone to join. So please contact me if you'd like to hear more. These are our wonderful participants, and at this last stakeholder event, we were all pretending to be our favorite micro and nanoplastic. So we also have a lot of fun together. I think that's really important. So I thank all of these participating organizations, and thank you all very much for your time. I hope maybe there's a minute or two for some questions. Thank you.
Thank you very much, Juliette. That was fantastic, and great to see how joining forces and all those institutions coming together was so impactful. I can see Junli has a question. Yeah, feel free to ask away.
Hi, Juliette. It's nice to see you again.
Nice to see you.
Yeah, and I was really interested in the standard, the reference like microplastic you mentioned, and then I was just wondering like how can we access that? You are gonna to sell it, or like how? I was really interested. I think
Yeah. So I was just I can put you in contact with my colleagues at TNO who generated these plastics. I should say though, we don't have many left, unfortunately. We distributed to so many partners.
I know. Yeah.
But I think that TNO is now thinking about how could they maybe make some more, or we're also working together with chemists at my university, at Utrecht University, who have developed a method within the European Aurora project to generate micro nanoplastics more from the bottom up. And so that's where we may have some more plastics for you. So please reach out to me. Okay. And we'll talk about that, because I think it's one of the biggest challenges of this field is to get reliable and well-characterized reference particles for testing. Yes.
Definitely. I will keep in contact, maybe end of the year. Sounds like that. Yeah. Okay. Thanks so much, Juliette.
My pleasure.
Okay, excellent. Any further questions at all from the audience for Juliette? If not, maybe I can finish with a question as well. And I think you mentioned the Aurora project there as another project that's been involved in activities looking to develop reference materials and standards, and it's something that we've identified in FHERITALE as well as being a real bottleneck, for everyone to be on the same footing. And now in Momentum 3 as well, you've mentioned the sort of forum for international involvement as well, and really joining these communities together to move forward in a coherent manner. So I guess my question is sort of quite high level, but what sorts of perspectives and from the earlier iteration of Momentum in terms of, you know, community building and reaching out to disparate research communities have you taken forward, and is there any, you know, learnings in that particular area of how to get people on side and bring people together that you can maybe share for us?
Yeah, thank you. I think it's still early days for us. What we've done is with the current community, which is, you know, those 30 organizations that are already involved in Momentum, we spent quite some time to talk with each other to decide how would we actually like to stay together as a community. And from that, this collaborative network governance structure, governance form was decided. It's really based on voluntary participation, but it's sort of semi-voluntary because we realize that if we don't have some sort of commitment, that it's really hard to really make agreements with each other and rely on each other to move forward. So we do have like a very light type of agreement with each other. How do we want to work together? What sort of governance structure? Like we've created these what we call working groups, and what we'd like to, the working groups for now are very limited to risk assessment and health effects, but there could be so many different working groups you could think of, right? For example, reference materials or analytical exposure assessments. So that's where we would love to have new partners join, and you know, people who have energy and to invest some time into bringing people together around a certain subject. So we're just starting, and we're hoping that by spreading the word that we have this Dutch consortium, this collaboration that we want to join with others, that we'll find ways to join. And too early to tell you yet if that works, but I really hope it will, because I think we have a lot to gain by forming a stronger community together. So I should say that I need to get to know FHERITALE better too, and how we could reach
Yes.
out to you, and maybe you could help us, you know, or we could help each other. With
Absolutely.
Forming
definitely.
forming a working group on reference standards, for example.
Yeah, definitely opportunities, I think, for us both to follow up after, and for sure, yes, we'll make sure to do that from our side as well, of course.
Thank you.
Wonderful. Okay, well, we are slightly over time, but I think we've done well, and thank you very much to all of our speakers, and thank you to Juliette as well for that excellent presentation and very interesting information. I will close up just by saying that the webinar has been recorded, so if you do want to refresh yourself on any of the information, then the webinar will be available through the FHERITALE YouTube page and FHERITALE website, so you'll be able to catch up there. And I also want to say thank you also to our speakers who managed to answer questions in the chat. That's very helpful. We really appreciate that. And if you have any questions, you can reach out to us at FHERITALE and the website via the website. There is a contact address on the website that you can reach us at if you have questions. Please do look out for future webinars that we will look to host over the coming months, and we'll have more interesting speakers for you there. But with that, I'd say thanks very much once more to our speakers, and wish you all a good rest of the day and good rest of the week. Thank you very much.
Thank you.
Thank you very much.
Bye-bye.
Thank you.
Bye-bye.
Bye.